Just adding a little bit of these files, it will feel more new colors. We'll add profit later. All right. Well, I think in your interest, I should start this right.
Yes.
But what I will do is that I will not continue with the course material because they're relevant for the exam, but rather because three of you are missing. I will do the ANN, which is a bonus. Slide. Oh, you were not in the very beginning here. So yesterday I told you that I will tell you what is a neuron, and I will put some slides on that. So there are very few. I will tell you what they are. What is a network structure, very briefly, and then do a little implementation. Implementation can take long. Right? So some of the functions that I've written, I will post them online, and then we take them and use them. Right? Okay. So that will be. That is what I will do first. And keep the others come, and then we can keep. Alright. So this is the set of the slides. Which is called ANN, and this is called the bonus slide. So it's not, as I said, it's not part of the exam, but I want that you learn what are neural networks. They're very simple. I mean, the implementation can be a little bit hard to understand how to estimate it or how to train these models. But that's okay. So that also indeed requires a bit of time, so that if you want to know how the optimization is done or training essentially. And then we go on. Hopefully the others will come, then I will continue with MBatch, multivariate structure. So which is an implementation. And hopefully this week we will be done with all the psychometric stuff, and then next week I can do portfolio stuff. And sort of more financial sort of methods that we have on our slide. So first of all, when we go to machine learning, there are two classes of, or two types of models or approaches that one has. One is called supervised learning, the other is called unsupervised learning. Right? Supervised learning is a method where you have some inputs with some function indeed in sort of in the Nadaraya-Watson, we estimated it non-parametric. Okay. But one can also use non-linear models, like hardly non-linear models. Okay. So neural networks that we have are indeed one technique that help you link some input variables, some features, some conditioning variables with a response variable. Right? So because you have the response variable, you observe it, and we call it supervised learning. Right? So that is sort of the class of supervised learning. So we are in that class. But we also have methods which we call them unsupervised learning. Right? Unsupervised learning is that, for example, let's say you have some data and you want to do clustering on it. All right. So a priori, I don't know. Do you speak French? I don't know. Right? I don't know whether you speak French or not. So if I want to basically check whether you and somebody else actually speaks French or not, so that's a 0-1 verb, right? So say you speak French, the other speaks, the other three don't. All right. So I don't really know. But then you that speak French, then probably you have been studied in France, for example, right? Or maybe in Belgium, somewhere where it is people are speaking French, right? And then the others may have been actually somewhere else. So there are some features that help you understand, potentially these guys speak French, and those not, right? So from those features which include some information about the behavior of you, then I go and understand the nature of clustering without really knowing whether you are a French speaker or not. I may go wrong. For example, you may have been in France and then I studied in Sorbonne in an English speaking program, and you know French, right? Or something like that. So I may go wrong, right? And so depending on how long you have been in France or what you have done in France doesn't really mean necessarily that you speak French, all right? But it's an indication, and that is the information that we can use to infer whether you speak French or not. Because we don't know the output, all right, then this is called the unsupervised learning. Essentially, classification problems are generally unsupervised learning. All right? So what I'm doing here is supervised learning first. Well, of course, we can use them for unsupervised learning too, the neural networks. So that is one more. And well, let's say how things actually work in neural networks. All right. Well, here we have some features or some variables, conditioning variables, and then somehow they come and then become x, sort of the response variable y. Right? So the network actually gives us has some inputs, and this is something that we want to predict because we have, I have a y, so y is observed for me, and then I have a y hat. You know? So y hat is actually a function of these guys with some transformation in the meantime. Right? So somehow these input variables are transformed, right, such that I have a y. Right? So these guys that we have here are that's something, so if you look at that's a network, right? And then we say that it has a structure, right? The structure is that it has an input layer, right? So that's where things are. So given here, so that's sort of the input. We have an output layer, right? And we have a hidden layer, right? This is something we should call it a hidden layer. This is just one layer, one hidden layer, right? And sort of, well, as I said, so y will be actually just a function of these, through all of these arrows and these nodes. So each of these nodes actually do something. Right? But let's see, can I see your hand? And can I see yours? So, wait a moment, so you are a little softer. Right? And he's a very tough guy. Yeah. So it means if I'm sorry, but this is an experiment. If I pour hot water on his hand, then maybe he will be a little bit longer staying. Yeah, it's okay. Takes some he's trained differently compared to you. So his neurons, his make is different from how you are. So, and that is because of the structure of the neurons that you have, and they are different. So neurons actually work like, somehow like this. So it's okay, it's okay, it's okay, it's okay, and then you take it away. And then let's see, so this reaction that we have to some output actually, well, can be modeled mathematically. And sort of the differences that you two have also can be separated from each other. All right. Well, for example, let's say we have an output. So let me now go ahead and give you a model of a neuron, a very simple one. All right. So let's say we have here heat comes in. So that's from the water that I'm pouring on the hands. It's not hot water, so you don't need to pour it. So that's heat that comes in. And then, well, this heat is actually first multiplied by some weight. So WH. W is weighting. So it's weighted. And then it comes in. And then there is another sort of constant which we call it the bias. It's not a bias in the classical sense of the statistics, but in neural networks this is called a bias. And then an output comes out. So this output will be a function of WH plus B. Right? So B, you can think of this as, so if your B is 2 and then his is, hers is say 1, then it means that, well, you're different. You react to this heat. So that's the reaction function. That's the reaction function that we have here. And that sort of controls sort of some differences, sort of shifts the reaction function of that. So, well, let's maybe take it very simple, and then choose p of x to be x, the unity function. If I do it that way, then this will be what? Then what? Out of these guys, then it will be WH plus B. So that's what we're going to do. That's a linear function. That's a linear regression. So W is the slope, H is the input, and B is the intercept. So that is what we have here. But then we have to, let's go back to this heating stuff. So, well, let's say we change this phi to some other function. For example, I say phi of x is equal to maximum of 0 and x. So, what is that? So, what is maybe this function? This one is very easy. So that is like so. That's a 55 degree line. That line. And let's look at this. So it is something like this. Alright, so negative and positive. And this one is a little bit different, right? So that is the x and y axis. Right? So that will look like so. So this is 0, and then afterwards it goes up. Right? So well, if the heat is low, if it is cold, maybe then you will not react. You will not do anything. So this is so nice. You stay on the hot water. Whether it's hot and then cool water, then you will not react. And afterwards, when the temperature goes high, then you start to react. Right? So this is a rectified linear sort of. Well, that's a simple function. I will give you the names. Right? The sort of properties. So that's another function. So these are the activation functions. Well, I mean, this phi can take other forms too. So depending on the type of the neurons. Right? For example, let's say the reaction function that we have is sort of, maybe it is looking like so. Right? So no reaction, no reaction. Right? And then sometimes the reaction function will be smooth. Maybe coming like this, and then slowly goes and then becomes, so from 0 to 1. For example, let's say, so you know profit and logic models. Right? So what is the function of the logic? That's the logistic CDF, right? Which is 1 over 1 plus e to the power of minus x. So that's the logistic regression. Logistic basically function. Right? And how does that look like? Well, at 0, so The reaction function that we have here is also the tangent to hyperbolic function, which can be negative, can be positive. But also it's a smooth. With the stars, and then the smooth equals to 1. Right? So, and so on and so on. So these are some very generally or more conventionally used tangent hyperbolic function. I will draw these pictures and compare them so you see how they differ. Right? So that is what we have. So if you have, say, a logistic regression, right, then the output layer, because that's also somehow, that's a node, so that's a neuron. So this one should have which of these functions? If you have a logistic regression 0, 1, you apply for master, you are accepted, rejected, so that's the output, and it's really good. Well, let's say you apply for a pass, then you have your GPA as an input, right? Maybe they will ask you for, what did they ask you? What did they ask you? When you were admitted to the master's program. You have to take a test. So the test is scored. And that's it. You take the test.
English proficiency.
English IELTS.
Yes.
What is the value? The minimum?
Six.
Alright, let's say. Alright. And if you have, so if it is 5, then you're rejected. But let's say your test score is very high, and you may be accepted because you're good, but you can't speak English. So I don't know. Somehow maybe. And then what else? What else did they ask? That's it?
Yeah. Motivation.
Motivation.
And
Well, that's textual stuff. That would be very funny to actually go on and into it in the machinery.
research proposal.
Research proposal. So research. Proposal. And what did you propose?
Something about getting on track and developing.
What were you?
I learned about like the fluctuation and something behind the fluctuation of the gold gold price and also the crude oil because at this time the war between Russia and Ukraine happened and check it out.
Sure. Oh, that's very nice. What about you? Yeah, that's interesting. But that's hard. Yeah, but then, good. You?
I think about how to raise fund for S&D in Vietnam.
Raise funds.
Yeah.
And what does it mean? So you raise funds so that you buy S&P 500 or what?
I need to have the capital. Yes, because S&D, some S&Ds in Vietnam kind of startup, they have a really nice idea of their product, but ultimately that somehow they don't know how to raise fund.
Oh, that's interesting. So it's sort of more management side.
Yeah.
So more understanding, so interesting. And you, what do you want to do?
Evaluation.
Oh, that's interesting. So the evaluation methods, right? Okay. Yeah, well, I mean, what method exists, maybe which is better, which is not, and so on and so forth. What do you want to do? DG. Dynamic General Equilibrium. DSG. Dynamic Stochastic General Equilibrium Model.
Just small topic about the history of free finance interest rate from State Bank.
Okay, okay. So your topic is also sort of similar in terms of management and understanding of this stuff. But the other topics actually they are you have some input and output. Alright? So you have inputs, outputs. And then you need to basically maybe link them. For example, which evaluation method is better. Somehow. Right? One is good, one is not bad. Maybe that is a classification basically problem. Let me go here. Right? So all of the questions that you have could be looked at in here too. Right? Maybe not the management ones, that may be a little harder. But all in all, so sort of the people here in VGU actually decide based on your values, should we admit the person or not? So that's sort of what we have, 0, 1. So these are the inputs or the features. They go in the network, right? So something happens to them, maybe many layers. Also, and then there is an output which is either 0 or 1. So, now these are neurons. So they basically they take these inputs, all of them they come here and then sort of they're rebated and then come out. So if you have here a 0, 1 variable, that's like a logic problem. Right? Then you use the logic reactivation function for the last thing. Okay. So and so on and so forth. So basically one can say, okay, what type of problem do I have at hand? And then you start going and then choosing what type of reaction function I would like to have. Right? So for most of nonlinear actually relationships, this works. And this is a good one. It outperforms the others more or less, like in terms of loss or cross validation and so on and so forth. So that's a good one. Right? And so that was sort of, I just wanted to tell you that, I mean, how to choose those, what to think of them, or what do they do for us. So, well, I mean, that's a simple regression stuff. So everything is linear, so there are a lot of regressions, linear functions, so each node that happen, and afterwards then you have the output. Right? Now, what? I mean, that was the reaction function. Now, I mean, so each of those nodes, or sort of the stuff that I have here, indeed, well, these are the inputs, and these are neurons, and each of them actually takes a weighted sum of those plus a bias. Alright. And then sort of the weighted sum goes into the reaction function, bias is added to it, the mean, and then you get an output. The output comes from this node. And then this also combines all of those with the weights, right? Passes them to a reaction function, adds a bias, another bias, that's a different neuron. And then, so you get an output. So you will have here and there 2 outputs from here. So this combines those differently, and then they are also again coming and combined, and then you get the output. That's how neural networks work. So let's look at the math, right? So very, very briefly, let's look at the math and then see, how things work. Right? So let's say here we have 3 inputs, x1, x2, and x3. And so here, as I said, so I mean, the network that I have here has just one hidden layer with 2 neurons in it. All right. So and then let's see. So here we have x1, x2, and x3. All right. They are pre-multiplied by a weight function. All right. And then we add the bias, and then we have the output of the first layer. All right. So let's see how this actually works. So here we have x1, x2, x3. So then we have 3 nodes. So we just write the network structure up, and then do the calculation of the math down, so that we understand sort of how these weighting schemes actually work. Right, so here we have x1, x2, x3. And then we have, so here h1, plus a bias. Alright, so they basically plus B, say, and they come here. And then let's basically give them an index of 1. Alright, so these are weights for the first neuron. Alright, and the same thing actually happens down there. Alright, so here I will have the other ratings, so sort of the other values. And we have a W for the second. Alright, but let's see. And then when they come out, then they are passed through an activation function. So, but let's see how they work. Well, here, then we have, say, Z, well, as a vector. All right, so let's basically have these two together. Z1, all right, will be equal to a radius t. All right, so which is 3 by 2 inverse. All right. Now let me write it 2 by 3. And let me bring in the weights. That will be W1, 1, W1, 2, W1, 3, W2, 1, W2, 2, W2, 3. So this is multiplied by that, then you have the weights part. And this is multiplied by that, then you have the weighted sum of what we have now. Alright. So this is a 2 by 3 matrix. This notation, which is in line with how Python actually does the programming, then the weights are, well, the inverse of what I wrote. So they're not 2 by 3, but rather 3 by 2, and then the inverse. So that is what we have. Times x, and then plus the, so that's 2 by 3, this is 3 by 1, so the whole thing is 2 by 1. And then here you have 2 biases, B1 and B2. Alright? So if you come to think of it, then this Z indeed is W11 times x1 plus W12 times x2 plus W13 times x3 plus B1. W21 x1 plus W22 x2 W23 x3 plus B2. Alright, so this Z1 actually has these two forms. Okay. So now we want the now the neuron took the input from sort of here, linearly, and then what happens is that now we want to know what comes out of this. Right? So there will be some output of this neuron that comes out. And this will be, well, I mean, phi, the activation function, evaluated at, let's say, the second element of Z1. Alright, that will be the output. Let's call it A. That is A1 and A. Right? And then here we have phi of the other one. Right? That will be phi of Z1, 1. This is Z1. Right? And has two elements. They are passed through these. That is actually part of the neuron, but that is what happens. So now they came out to two values. Alright, so this is also like that. Alright, so they all come here. Weighted sum, the activation function works on it, and then you have 2. Alright, so here we have 3, now they become 2. And these 2 should also again be combined. Alright, into 1. Alright, so we need to combine them into 1. But that doesn't matter. That was 3 to 2, now we have 2 to 1, again we need weightings. Alright? And these are the weightings. Alright, so that's sort of what I have in the last basic part. they are weighted, and then a bias is added. Then you have the output. So you see, so sort of that's a lot of weights. Right? It can happen. Plus a lot of biases that they do on, and then they get us the output. Right? So can you write? Let me write it myself. So here the output that we have will be, well, W2. So here we have some weighting, so let's say 1 on layer 2, right? So here, so this should be multiplied by 1. And then plus W some other weight, 2 at the second basically level of weighting, right? Times A2, and then another bias. Let's call these biases at 1, biases at 2, at 1. Right? Now here we have just one bias, because there is just one output. So that sort of gets out. Right? So, so here the transfer function that we have actually is in there. It is in this hidden layer. Alright? That is what we have here. Alright, so that's just once that we use this hidden function. Sort of that I did basically say what it is, what feed is. Should I use this, and that, or whatever. But the last basic layer that we have, that's sort of, I'm actually taking it towards a regression. So here, in the last year that we have this to be that. Phi of x equals x. Right, so whatever we have, then the same thing, that's a unity function. What is it? That's the 45 degree line. So y equals x.
So at the
Okay.
end you have y.
Sorry?
When we combine A1 and A2,
Yes.
and we have y.
Exactly. So here then we will have essentially y. Right? So this y hat is this. So that will be 1 times A1, that will be 2 times A2, plus a b, then we get y. Right? So that's sort of, well, if you come to think of it, you can now write it out. Right? We can write all of basically this stuff out. Right?
But why we just started W1 and W2, I mean the sign of W.
This.
No. Yes, the W, the sign, the 2, 3,
2 by 3.
yeah, 2. Why not 3 by 2?
Because here we have 2 lines.
But why we just have 2?
You want 3. We can add.
So that we can choose.
Yes. Now I will do CAPM, I will choose 20. I will choose 20 because I mean the more, this you are jumping ahead a lot. Very nice. It's so much like what you do. But let's keep it simple so that you can understand. So that it will be a little bit easier. So what I want to actually do here is to tell you what happens. Right? So that is A, which is W1, the vector x plus B1. Alright, so that is, I mean, this function, I can write it like this. And let's look at this. So the output. Alright. So the output is so let's define capital Phi of x as a vector or sort of A. Alright. Let's call it A1 and A2. It is a vector. W1 transpose, which is like so. And that will be W2 transpose times phi of the vector that we have, well, capital Phi, which is indeed the vector function. W1, I will move it up so that you see people who are in the back. It's x plus b1. Alright. Plus b2. Alright. So that's sort of what we have. So, and then if you come to think of it, this is just a nonlinear function. Right? Well, one hidden layer. Well. So now, if I have two hidden layers, alright, then the dimension of this W will change. Instead of having 2 by 3, if I have 3 neurons, I couldn't show 3 without my feet. So let's, if you have 3 neurons, then this W that we have will be a 3 by 3. So 3 equals 3 rows instead of 2 rows. So that W can grow. And the dimension of this will also grow. It will be 1 more bias. If you have more layers, then the so nonlinearity, the way actually that you have things entering out in this functional form and then getting to the output will change. Right? Now, sort of think of making this one layer 2. Right? So if I have, say, 2 layers, right? So we just draw so here we have x1, x2, and x3. Alright, and then let's say we have 1, 2, 3, 1, 2, and the output. Alright, so this goes in here. Alright, so then you have the first layer with 3 neurons. These are connected. And then come here. Alright. You have to be around there. So then they also are connected. Alright. Then you will have the output. So this sort of nonlinear. It's a very simple setup, but it's capable of very easily generating a very highly nonlinear function. Alright. Because it's nonlinear, then the more basically neurons you add, the more nonlinear it becomes. Alright. Because of there will be a lot of movement here and there. It becomes more nonlinear. And then you can also add more of these layers. For example, let's say after 2, or let's say we have here 4 and 3 and then 2 and then alright, so that is a multi-layer neural network, right? So the hidden layers are 3. So with the dimension of 4, 3, and 2. Okay. So and each of them is a sort of neuron, right? A neuron also has this long stick attached to it. So if you look at a neuron, let me find a picture of it. Okay. Oh, okay. So that's the human brain. Well, which has actually a lot of neurons, right? And then they are connected. So the tip of your finger sort of is connected somehow with long wires to the brain. And then you get a reaction. And there are not one neuron, but rather many. Right? So the measurements say at the tip of the finger when it is about heat, and it measures many things. So there will be many inputs at every sort of point on the skin, and there will be another neuron. very linear. So you actually work with a very highly nonlinear way. Okay? And then the activation functions probably are not like this, but they're more complicated inside our body. But that model seems to be fine. It sort of works for a lot of applications that we have, or models that we have, modeling basically tasks that we have. So you talked about your master thesis. This was mine. My master thesis was on neural networks. It was long time ago, so I don't know what did I do there, but I still remember the methods. But now the thing is that, so sort of if I, there is actually, it's very hard to, because you have three outputs, and then the more layers and neurons you add, then there will be more and more parameters, because all of these W and the B's you have to estimate. Alright? So, another estimation, I mean, if you come, sort of, so let's estimate this. Alright? So, so if I want to estimate all of those W's, then I can do the following. I can minimize, then this is two layer, sort of one layer. So then you have y high minus y hat high. You sum it, take to the power of 2, and then you minimize in W1, you minimize in W2, you minimize in B1, and you minimize in B2. Alright, so that's sort of, these are the choice parameters. That was 3 by 2, this was 2, so this is 6. This was how many? 2, so we have 8, plus 3, 11, plus 1, 12. So there are 12 parameters to estimate. Okay? But there it will be a particle. So, I have some Spanish and colleagues, and then they basically talk about, say, horror. There's no error. They say horror. Somehow, even more horrifying. So that would be a horror indeed estimation model. Alright? So not that people didn't know these models, but then you needed computation power. Alright? So this actually machine learning became more appropriate, more usable, and people start using it since we have computers. Now we can actually go train such a network with many neurons, many layers, in a fraction of a second. Because we have computational power, then we can indeed do this. When I did my master thesis, we had problems in training with it. It was taking weeks so that you have one number. So that was, but now it is faster. But look, I mean, this is a minimization problem. And that's, the dimension is very large. So the mathematicians, or so the data scientists, have been very creative in understanding how to do this minimization problem. And there are different methods for doing this. One of them, which I will not actually talk about this, but because this is not part of your example, it's supposed to tell you what your networks are, it is something which we call the back propagation. Right? BP. Back propagation is a very classical method. And the way it works is that sort of, let's say you choose some weights and some sort of some starting values. I mean, when we do optimization, we have to always start from some starting points. You know that. Let's say we choose some random one, and then here you get a big error. So either you overestimate or underestimate. So error is large, error that we have here. But the error that we have here is actually due to how this neuron works, because maybe it has a wrong weight and wrong bias, or maybe the weights are there wrong, and so on and so forth. Right? So part of the error that we have here is because of the performance of each of the neurons. Right? So what this backpropagation does is that it takes the error in the very end and then distributes it through the network. Right? That's actually just intuitive. Yes, you should read the method for yourself. But I just tell you the idea, so that when you read it, then it will become a little bit easier to grasp. Sort of the this algorithm, in this backpropagation. So they adjust a little bit. This also adjusts a little bit, such that the total error that is there is minimized. Okay. And there are also other algorithms and so on and so forth. So in the implementation, you will actually see. Let me just use some algorithms, and then we do some estimation. Alright. So that's neural net. Alright. So it can be used for many sort of tasks. But I just thought, okay, that's actually very easy because you just fresh come from econometrics, and then you have an input and then an output, and you need some nonlinear function to sort of link these outputs to inputs. Should we do an implementation? I want to implement this. And estimating a CAPM. Yeah? Okay. I'm just looking at time just to see how much time I have to spend on that. But I mean, in the CAPM, so what I will do is that I will generate some features here, out of blue. So you have 3 features, and then estimate the capital. Alright, so here, for example, let's say I have the asset return T minus the risk-free T equals alpha plus beta RMT minus RFT. So let's say beta 1. But let's say I will add some volatility measures. We learned how to do them. Okay, so just bring it in. And then I will also beta 3 bring some function of time. Right? So because there may be somehow some variation in time that we have with this, close the error. Right? So that's sort of what we have. Right? But so to speak, in this framework, then, well, that's linear. Right? That's the y. Right? And well, the capital itself then has also this capital beta. This is what we like. Alright? We want to know it. But then here we didn't have any what is beta. There is nothing that we could call it beta because that's sort of that's sort of the actually then I did engineering, I didn't study economics. And I did numerical stuff, so that was sort of what I got. Differential equations and which I still like that. So when I came to economics, and people tell me what? Neural network, what the heck? Just do something normal. That was somehow, it was 2000 whatever, 4 or 5. Then I didn't touch them anymore. Okay. What? Then I did some other fun stuff. So I said time series, which is very good. I mean, but the reason that people were telling me because they wanted a beta, and this doesn't really want. Right? That's sort of problematic. But then, if you come to think of this, in the end, this regression sort of the let me write it up there. All right. So here we have a response, which is a function of x1, x2, x3, all right, plus some u. All right. So that's what we have. So if I basically can get this nonlinear, right? Maybe I can also estimate or sort of calculate the value of this with respect to say x1. Right? So that will be the slope essentially, which is the slope here. Right? Because we have enough power computationally that we can calculate this numerically. Right? You know, right? So that's sort of we can say, right, this is equal to limit. Let's say f of x1 plus some small number epsilon. x2, x3 divided by epsilon when epsilon goes to 0 minus f of x1, x2, x3, right? That's well definition of the derivative, right? Because that's a limit and we need epsilon to be very small, but we can choose epsilon very little. So say 10 to the power minus 6 or minus 4. And then perturb the first. So we add to all of the values that we have here the value epsilon, divide by that, and the other derivative. Right? So then we actually know R to get the coefficient, so the kappa and beta coefficient. Right? Good. So let's do that, okay? You have questions before I go on? You don't have questions? Sure, sure. Well, yes, I mean, you can always rely on machine learning methods, right? But this question you could ask me after you know the classical ones. Yeah. And if you didn't know them, then you wouldn't have said that, so why should I use this? Okay. But this actually is, well, though it is okay, it's very flexible and so on and so forth, but it somehow there is a big force, right? So there is a big power that wants this beta, right? So academic industry and so on and so forth, they are happy with this beta. It has a meaning, right? It's the exposure and the stories you know from far. Right? So that's sort of what we have, right? So, well, as I said, so if you didn't actually do this, if you didn't understand the questions, then you couldn't say maybe this is a better one. Right? That's what we have on the very first step. And then on the other hand, they come with problems, these neural networks. And they also, what they are called black box systems. For example, this is very hard to do inference. Is beta 0 or not? Yeah, so let's say you have y equals a plus bx. And then you want to test, so that's an economic question, right? But whether this variable has an effect on the left-hand side variable or not. That's a hypothesis test. And that's not so easy to do this, to do it in here. It's not possible. It's somehow, that's not possible, but it's not easy. So the theory is still to be developed. Maybe in some years then we will be able to do testing. Right? So going to testing, well here I will not go into testing with you, right? Because we need, for example, you have to know how to bootstrap. And then how to bootstrap something you don't know, right? So I'm not saying that these models are good, and I'm not saying that those are good. I'm saying we have both. And then let's apply them and let's see which one actually gives a more sensible result. Something that is making sense. Right? Well, and oftentimes the relationships are well approximated linearly. Right? Most of the times, you can approximate the relationship between variables in a linear model. You can approximate, the approximation is not bad. Right? So behind local linear, for example. If you have a trend, you take it out, and then you are left with a very simple linear model, which is good and it works, and somehow not beatable. Right? So our models, ESG that you want to do, they are not beatable. They are good. Right? So they're good for forecasting. And we say central bankers actually use it for forecasting, say inflation, for forecasting GDP growth, and so on and so forth. And they for sure know the other models. If they don't know, then they can hire someone who can do that for them, right? There's not actually a big problem, right? But because they are simple, they make a lot of sense, they are perched on macroeconomic theory, then they are good. Right? So sort of one doesn't maybe need to go too much away from them. Because they are simple, as I said, they're easy to estimate, one can do inference with them, and they work. Right? Not that they don't work. I'm not saying that I'm actually getting you a better capital model, right? I just want to, maybe we shouldn't estimate capital using a sort of an AN. I'm just using it as an example, as a demonstration. So sometimes the relationship is highly nonlinear. page. Alright? So the experience in the beginning when you start a job, then the experience actually is value. You learn. Alright? And after 2 to 5 years, then you learn more. But then there is nothing to learn. What do you want to learn? Sort of if you're in some department in the bank. After some time, then the sort of employer doesn't give you any more bonus because you learn more because you did it. In the beginning, the experience actually has a big effect, and afterwards, sort of becomes smaller, looking like a log function. Alright? So it means that oftentimes these simple transformations work, and they are in line with our intuition. So we don't need to turn to something very hard to be done, which is hard to manage. Right? So that's number one. And then the other basically issue that makes this even more complicated is that, now you will see. For example, let's say you have a very simple sinus curve, and you want to estimate using this basically stuff. Then you will need a lot of, you need 2 layers and many neurons, so which is very complicated. But then you can estimate roughly using 4 lines, and that will be roughly good. Alright? So linear functions are not bad. Alright? They're good approximations. So it's not that they are obsolete. They are good. Now these are can be not to
I think from William's question, there's like, to me, like, I'm thinking about whatever happened in the world, so it has many like like so many variable effects on the things, so I think like, so that's why I come with the question like, the neural network like model is so powerful something.
That's true, it is used. It is also used. So, for example, let's say, well, in the field of digital marketing, right? So, which is something that, say you look at Amazon, you want to buy something, right? Then, say the number or the amount of seconds or times that you look at the product, you look at it, and that's a very interesting picture you click on, right? So that is actually some variable which seems to be interesting and important when it comes to market. Right? And how that will be a non-linear effect. So how we work, right? So how a human actually works when it comes to choosing or selecting a variable. Right? So in that framework, I'm not saying no. I mean, you can go and then do whatever you want. Right? So I'm not saying that these are bad. And you may actually have many variables. I'm saying that they come with complications. Right? And with sometimes unnecessary complications. For example, well, okay, so if you have many variables, then we know how to deal with them. We shrink them. Right? If the information which is in there is important. Right? And then we sort of, when we shrink them, then we can do the simple linear regression. Right? If you don't want to do shrinking, then maybe yes, and sort of combine them and so on and so forth. But if you come to think of this, then the first is that, let's say you have 100 variables and 2 layers. Right? Or sort of 3 neurons, 10 neurons. Right? And what you do is that this 100, 120, which are the inputs, for example, let's say for GDP calculation, they become in the end 3. They become 4. Right? And that's a linear combination. Well, so you have, say, where is it? So here, is the very first layer. So we had 3, and then they became 2, because we formed a linear combination of the first and the second. So that's also a shrinkage. Right? So we know how to do this. That's the principal component of these layers. We'll talk about that later. So these methods that we have here, though this is non-linear, but that's not so different from other logic that we have that could simplify the matters, and then so that a linear approximation will be good enough, right? And then in real world they are also used, right? So a lot of things that we have are actually virtual machine learning methods. ChatGPT, that's a text mining also, that's a text mining, so that's a language model, right? That's also a machine learning. You couldn't do it with linear regressions. But linear basically is trying to machine learning methods, so that you could implement such a model, right? But text mining would have been, that probably would have great interest in these guys, and then maybe expanding and learning and so on and so forth. And then using them. I'm not saying don't use them. Alright? Use them, but be careful. Alright? So that's sort of what I'm saying. Because they're not free lunch. Right? So whenever you see there is a free lunch, then there is a stick also on top, so that if you take too much, they hit you. Somehow like this. And by so the reason that I introduced them to you is that to tell you these exist, use them. Right? But also the other ones that we have had so far, they're also interesting and important, and we have to use them too. Right? Because they tell us something interesting. They tell us something about the dynamics. They help us do inference. This is not. Yeah. Good. So let's just start with the linear. Well, if you remember, we did what did we do? We did some CAPM, right? Alright. So there was this CAPM model. Okay. CAPM regression. So where we get the data and so on and so forth. And we take that, the beginning of this basically file. So, very good.
Yeah. This is a little bit cool.
So I will take the beginning of this till merge data. So it connects, gets the data, and sort of calculates everything because I have y and x. And then afterwards I will continue with this top of this model using a neural network. So I will teach you how to implement that in Python. Okay? So we go to this CAPM file, and then we get everything up to the merge data. Alright, so up to the merge data where we have everything, okay? And go here. Alright, so that's sort of what we have had so far. So, well, and then here we need some packages. Alright. Which are, well, I mean, so they come from a scalar. Alright. And this has a part that we need to be bigger. Alright. So which is the neural network. The model is based on neural network. Right? And then from that we import, we want to do regressions. We import something which is called MNP regressor. Okay. So MNP regressor is indeed, well, ML stands for multi-layer. P stands for perceptron. Perceptron. Each of those is, well, that's a perceptron. Okay, so that's a multi-layer perceptron regressor. Alright. Because that's a regressor, then the last activation function will be this. Here. Okay, so that's sort of what we need. But we can change these, so depending on our needs and so on and so forth, right? That's number one. Well, oftentimes when we do neural networks, right? For example, let's say this is the market index, market access return. So this is the market access return, okay? And then, well, these are some other variables. For example, let's say, well, the returns actually are a function of the volatility, from finance. Okay. So then I will actually add the volatility conventional, that one normalizes those variables. Right? So, and also this. This I will not normalize. Right? So I will leave it as is because I want to basically see if this changes by infinitesimal, so by a small amount, and how much the result will change. Right? So this I do not escape. Right? But the others I will. Or maybe this case it doesn't matter. So that's sort of what we have in general. I mean, you have to be careful with this scale. So here a scalar also has a pre-processing sort of part, alright? And then from that then we can basically bring in a standard scalar. So that's a class that helps us scale basically variables. Alright, so that's sort of what we do. So that's the only thing on top of the previous stuff that we have. I brought this NLP regressor. Okay. And then let's run it so that the data come and we get the risk-free rate and so on and so forth. So that is what we want.
Professor, can you scroll up a little bit? Data.
Okay. So I can go on. So well, let's just start with sort of getting some variable for our analysis, sort of what we would want to do. Let's look at NVIDIA, UW, equity, yes. All right. So and then let's calculate. So that's the y. Now let's define y. So y will be merged data. Alright. So ticker minus merged data and DTB3. And let's define x. That's also merged data. But that is the SPX index. Alright. Minus the risk-free rate. ETB. Okay, so that's sort of what we have here. Now let's just start with preparing data for the MLP. Alright. Well, let's go on. Well, let's see. I will just rename them so that things are a little bit easier to access. And I want the volatility. So this volatility I need to have two. Well, we can get the volatility using a rolling window. Right? So rolling window volatility I can just get and then pass it to the to this here. Sorry. So for that, well, let's use a window length of 20. Okay. And then let's define a DF, the data frame for the ANN, for the this neural network. So I will have a data frame and put the data in there so that it's easier to work with stuff. All right. So let's start. All right. So here we have DF, ANN. So first, let's basically have the asset excess return. That's the excess return of the asset. And that is equal to 1. Alright, so that is what we have as a y. And that is the asset excess return. Then we have an x. Market excess return. So that is my x. And then let's add the volatility. Vol, let's put it vol. And that is equals 20, then gets me a standard deviation. But we could do the standard deviation, we could use a large deviation. But I use it very simple. So that's a feature, right? So that's one variable that I want to use to sort of, well, as a little exercise. So that's real. And then let's add time. Right? And that will be in P of a range of len of say here. Alright, so that will be time. So 0, 1, 2, 3 up to the end. Well, I mean, that's the data, but let's maybe scale the time. So it's not a number from 0 to 10 or 6,000, but rather a number from 0 to 1. I don't like to have big numbers. Because if they are big, right, that's actually important that, right, it doesn't matter if you come to think of it, right, so that you scale it or not, but for optimization, it does matter. Okay? Because look, I mean, if the weights, say I have some feature numbers, if it is too big, right, so the value of this stuff, or I should say, if I'm talking, you're typing. The one that you, oh, I should do, you see it. Actually, you should have been here. Or somehow, because most of the time the program there, we have to look like this. I wait so that we type. And we should also have our break. No? Such a problem. You teach and then time finishes and then you want to do more.